All right, folks, here's our gasp second to last chapter of the year. That's so crazy. You're probably like, what are we going to do for the rest of the year? Well, after vacation, we'll move on to chapter 21, and then we actually start our final project, which is nuts. I'm going to try to throw in some activities, but obviously if you don't have the resources available for it, not a big deal. I will just give you data for it, so not the end of the world. Anyway, I want you to start, by doing this warm-up from chapter 19. Just a reminder that chapter 19 was all about means, whereas chapter 20 is going to be comparing proportions or means, so it's going to kind of combine both. So try the warm-up, which is based off of a homework question that was in your textbook, but try it out and then I'll have the answer in a few minutes. All right, here is the work done out. So you have to assume randomization. The months represented is less than 10% of all months in this case. The nearly normal condition is fulfilled because it looks pretty unimodal and symmetric. For letter B, you end up with that mean of 20.08% and the standard deviation of 4.09. So you can just use those numbers. Just a reminder that if your n is 144, your degrees of freedom is 143. So when you plug this into your formula, the t-score you can get from either the t-interval itself, or you can do the t-model, so a t-test. When you add and subtract your standard error, which is your standard deviation over the square root of n, from that mean, you end up with 19.4, 21.75. So you could say you're 95% confident that the interval from 19.4% to 21.75% contain the true mean monthly percentage. So what's weird about this answer is it's technically a mean, but they look like they're proportions, so that's the only strange part. You still use the mean formula. Oh, instead of 21 point, that's weird. So it should. All right, so these are our first half of our notes. So we're gonna run through them together, and then tomorrow you'll get the second half. The other thing is I guess they made a typo in the answer key, so that should have been 20.75 instead. So if you got that 20.75, not 21. Interesting. Okay. So we're gonna go through something called the ruler for statistics. So it's kind of weird because you guys have seen this before. It's the Pythagorean theorem of statistics based off of standard deviation. So say you have two different samples. Unlike paired data, it's from two different groups. So it could be like males versus females, something like that. The nice thing is the variance of those added together is just the variance of them separate, okay? But when you're talking about standard deviation, because it involves squares, the standard deviation of one plus the other, you have to use the square root of them squared. So it's a slightly different formula for your standard deviation. The next thing that we're going to look at is the standard deviation of the differences between two proportions. So again, this is not like paired data because it would be like males versus females or two different countries, something like that. So what it ends up looking like is this. So your standard deviation of two different proportions, the difference between them is the square root of them, basically the standard errors separately, if that makes sense. So you add them together and then square root your entire answer. All right, we're going to do a little example so you can see it done out. So find the standard error of a difference in proportions. The survey had 886 randomly selected teenagers. Found that more than half of them have online profiles. Obviously, that would change by like everyone has them now of some form. Notice they always have they have MySpace on there, which most of you have never even seen. But they do have a lot of the same things like Twitter, Facebook. They don't have Instagram on here. But what you're noticing, hopefully, is that they're looking at two different samples. So they're talking about boys and girls as two separate groups. So what you can do is find the standard error of one, aka the boys. Find the standard error of the second one. The easier thing to think about is that the formula for your standard error for each of these, if you're putting it into the difference formula, notice that you're squaring them. So that's going to be the same thing as literally just doing this plus this and square rooting them. So notice because you square the square root, it goes away. Okay, so you could actually just plug what's underneath the radical in instead if you prefer. So it doesn't really matter. But notice you end up with a standard error that gives you a difference between the girls and boys. So it's a slightly different scenario than paired data. All right, so independent groups assumption, super similar to what you guys have seen. The only thing you have to add is that literally the two groups, so the two groups of data. So in our case, for the last problem, the males and females would be are independent. Okay, so this is going to feel very familiar because it's pretty much the same stuff. They just throw groups in front of it to show the difference between two sets of data. And then what's nice is you can keep the original assumptions we're used to. So they are using that example that they used before to just show how each of these are fulfilled. Some of us are still not being specific enough in our assumptions and conditions, so make sure you read through these. You might want to pause the video to see how it works. You also need to calculate your success failure here, so it's 248 for the boys times the 57% that they give you. So you have 141 that are going to be greater than 10, and then the failure would be 107. So you actually have to calculate those, not just say what they are. Excuse me. I think that's good. If you can read through, let me know if you have questions on what they're actually asking you there. But all right, confidence intervals. Again, we're coming back to it. But again, now this is going to be for two groups of data. So the nice thing is a lot of the information hopefully looks the same. So this formula hopefully looks a lot like what we had before. Just a reminder that your standard error is now that. So the z-score you still find the same way based off of the 95% confidence rule. So a lot of the information you're going to use is still going to be the same. Remember, with a proportion you can use z-scores, and with means you use a t-value. So we're kind of going back and forth between the two. So now they say a two proportion z interval if you want to find a confidence interval. That's why we can go back to 2 as your z-score, because we're doing a 95% confidence. This is a z. And if they were talking about means, you would find the t-score. Notice that for the first part, you just literally subtract the proportions. As long as you do it in the order that they ask you to, you should still get the same answer. So you're saying that we can be 95% confident that among teens amongst age 15 to 17, the proportion of girls who post online profiles is between 4.5 and 21.5% higher, and that's because you said girls were going to be first in this. You would end up with negatives if you went in the other direction, so they would be lower. So if you did boys first. So it seems clear that teen girls are more likely to post profiles. I still think that's fairly true, but again, those percentages would be a little bit different nowadays. All right, so now is the time we're going to practice in the graph and calculator like we've done a few times. But again, this is going to be for two different sets of data. So I'm going to zoom in a little so you can see it. The biggest difference with this in the last few units is that now you're doing a 2 proportion z interval. So a lot of this stuff is in the same position. You just start choosing a different option within that. So you're still going to stat tests, but now you're choosing a 2 proportion z interval when you're given proportions because you have 2 sets of data. Again, notice what they plug in for these values. It's what they calculated in the last part of the problem. So the 142 they actually calculated for us before, but you can see that they do, that's your number for your x values. And then for your y values, it's going to be the 73. So this is back to that confidence interval for what we just looked at. So the poll revealed that 28% of 506 men, so you have to do 28% of 506, and that goes in for your X. And then for 14% of 520 is right there. Okay, so that's where all your values come from. Notice they actually get your P, your proportions for each sample, which is kind of nice. You can see how that looks. And then they actually give you the interval for you, which is very convenient as well. Okay, so obviously you can't follow the directions here unless you have like a friend that's been staying with you that's on the other side of the room for some reason. Or some of you have siblings taking stats as well. But I want you to try this out, see what you get, and I will have the answer for you in a minute. All right, folks, hopefully you were able to interpret that confidence interval, but it's saying that notice it's a 90% confidence interval, not 95. So we're 90% confident that if members are contacted by email, the donation rate will be between 4 and 18 percentage points higher than if they receive regular mail. So you actually have to do 11 plus 7 and 11 minus 7 to figure out your interval there. And obviously those would be very different nowadays. It would be much higher for email. All right, we are almost there. So just a reminder for you to do a 2 proportion z-test, which is kind of like what you just did, but now it's for hypothesis testing. It actually looks very similar to paired data because you're doing P1 minus P2 equals 0 as your null hypothesis. Your z-score looks, again, super similar. They just remind you of the standard error for this. And then you can use, again, your calculator, but you can do a 2 proportion z-test. Again, notice it's 2 proportions because they're talking about 2 sets of data. So their example was people who are snoring. I apparently snore since I'm pregnant, but it says that 811 people over 30 years old did. 318 snored, of the 811. And then 184 of the people under 30 who did. So, and that makes sense because younger people tend to snore less. But I want you just to look at the mechanics behind it. So notice that their null hypothesis here is based off of a 2 proportion z-test. So anytime you're doing a hypothesis test, you have to choose a test, okay, which is number 6 on your screen. They also gave you the same information as we did before. So notice it's 318 out of the 811, and then 48 out of the 184. So those are your initial. Your alternate, unless they state otherwise, is going to be does not equal. So usually they have it in the question, but it says, what does this mean about snoring and age? If they ask something about like one of the groups being greater than the other, then you would choose the other 2 options. But notice they give you all the values here, and they do a lot of the work for you. So feel free to plug those in if you want to try it. Otherwise, we are going to move on to the last real example of these together, and then I'll have you try one on your own. Okay, so again, they're talking about internet safety, aka how many of them have online profiles. Notice their alternate is it does not equal 0 again, because they say, is there evidence of a real difference between boys and girls? So they don't say one way or the other, whether one's higher or lower. If they did, then you'd want to say greater than 0 or so on. You could also set these up as like probability of boys equals probability of girls, because if you add it over, it's the same thing. So if that makes more sense to you, feel free to use it. They check all the assumptions, conditions. Make sure you note they plugged in for the standard error again. Your z-score, all they have to do is take the proportions and subtract them and divide them by that standard error. So that actually gives you your z-score. And then as we're used to doing, you have to do your probability by doing your normal CDF when it comes to proportions. And in this case, you could do either the higher or the lower. Because they gave you a positive z-score, I would do 2.57, 99. that gives you one z-score. Remember, if this is a hypothesis test where it doesn't equal 0, you have two sides of shading, so this would only give you one of those probabilities. So you have to multiply it by 2 to figure out the whole probability, okay? Again, they say z is greater than 2, but also because your probability is less than 0.05, you would reject your null hypothesis, which means there is a difference in the proportion of girls and boys, which we actually found before in our confidence interval anyway. So it kind of reconfirms it for us. Just a reminder before we move on that if a t-score or a z-score conflict with the probability takes the cake. So most of the time they're not going to conflict, but every once in a while you run into a problem where they have slightly different answers. So you just want to be careful of that. Okay, I'm going to have you try the next example. And then I'll just like go over the means example they gave on the bottom, but most of the mean questions are going to be tomorrow. So I'm going to have you try this out. Sometimes it helps to draw the normal model, so that's a good idea to have that. But check out the problem. Again, they're really into pregnant women and fish. But this is talking about, again, proportions, so just be careful. So it's all z-scores and normal CDFs. Okay, so try it out, and I'll have the answer for you in a sec. Alrighty, hopefully you got it. So again, you can either write your hypotheses like they did. It's hard because they're both P, so you just want to give a little bit of subnotation for yourself just so you can tell the difference between them. Remember, you can always also do this instead. So they did P for MS, and then you could do P of P. And remember, those are for your magnesium sulfate and your placebo. So you can always do that. Again, if the alternate makes more sense as well to just like add both sides, you could do the the proportion of the magnesium sulfate is greater than the proportion of the placebo. The reason it's greater as well, just as a reminder, is it says, is this treatment, does it dramatically reduce the occurrence of eclampsia for women who develop the condition, have a greater risk of death? So if you usually look at the last statement, that tells you what your alternate hypothesis is going to be. Make sure you check your assumptions and conditions, so letter B. And then you want to say that technically they're missing the 10% condition, but you want to throw that in there, that the groups of women are less than 10% of the 50,000. And then for letter C, you have to find your z-score. Hopefully you got 0.81. If you didn't, look back at the previous page because it has the formula for you. But remember, you want to do your, in our case, it would be the probability of, your proportion of your people who had the drug, basically the magnesium sulfate, versus the placebo. So you have to do 11 over 40 minus 20 over 96 to figure that z-score out, divide it by your standard error. Okay, and then you also want to figure out your p-value, your probability for this. So use your z-score. Because it's a right-tailed test, you can go right to your normal CDF. And either way, we're going to fail to reject our null hypothesis, which means that there is no general difference, basically, between the data. So they're not at a greater risk. Okay, we're going to move on to our last question for today, which is comparing means. Just remember that if you know sigma uz, and then usually we're going to use t for means because we actually don't know the population proportion, the population standard deviation. So that's why we use t instead of z for our means, okay? just a reminder that your standard error is basically the same thing for this. So again, it's going to be standard deviation of the first one divided by the sample size squared, plus the standard deviation of the second divided by n values, and all squared, and then square root your whole answer. So this is just one example of the difference with means. I just wanted you to see how to plug in the values. So notice that they took your standard deviation for your first refilling of the bowl. By the way, this is a crazy concept that they just like secretly refill your bowl to see how much you eat versus letting you just eat how much you feel like you need to eat. It's a very crazy concept. Anyway, take that, square it, divide it by your n value, so that's 27. Take the second standard deviation, square it, divide it by its n value, and then square root at the very end. So they're saying that the standard error between refilling your bowl versus ordinary bowls, and this is for means, would be 2 ounces. So you actually, it looks like based off of standard deviation wise, you're eating more because it's higher when you are getting your bowl refilled, which makes sense because I would eat all day if they gave me a refillable bowl. All right, guys, enjoy the rest of your day. The rest of these will be posted tomorrow.